Okay, so this is the outline of chapter 29. So first we will introduce actually the B field generated by current, or how we can calculate the B field generated by an arbitrary current, which is so-called the Biot-Savart law. And then we will introduce the force between two parallel currents. Actually, this is an extension of the content from the last chapter. Okay, at the end of the last chapter, we have learned the second version of the Lorentz force. Okay, which means that if we have a current in a B field, then there will be a force acting on it. Okay, so here if we have two parallel currents, okay, either parallel or anti-parallel, then one of the current will generate B field. So this B field will be, so another current will be in this B field, so that there will be interaction between them. So that, and then vice versa, and then the other current will also generate B field, and then the original current will be also in this B field. So these two parallel currents will interact with each other. So this is somehow like the extension of the Lorentz force. And then we will talk about the Ampere's law. So Ampere's law is actually one of the law in the Maxwell equation. The last one we learned is the Gauss law, and then next is the Ampere's law, and then the next one is the Faraday's law. We will learn the Faraday's law in chapter 30. So these laws are quite important. And then we'll learn something called the solenoid and toroid, which is some structure to generate B field. And then in the next chapter, we will actually call a solenoid like an inductor, okay, an inductor, 电感. And then finally, we will talk about the current carrying coil as a magnetic dipole. Actually, we have considered something similar in chapter 28. So we already introduced something called the magnetic dipole moment. The mu equals NIA is actually this magnetic dipole moment. Okay, so we just recall this overview of electromagnetism. So we have the Maxwell equation. We will learn the whole thing in chapter 32. But actually, we have already learned Gauss law in chapter 23, and in this chapter we will also learn Ampere's law, and then next chapter we'll learn Faraday's law, and then also in chapter 32 we'll learn the B field version of the Gauss law. Okay, and just as what I mentioned in the last chapter, there is no monopole. Magnetic monopole does not exist. So on the right side, we only have a zero to make this thing much easier than this one. On this one, we still have some enclosed charge, but we can't have any enclosed magnetic monopole. Okay, so here we introduce how to calculate the B field due to a current. So we just jump into a complicated formula, something like this. Okay, so it says the magnitude of the field dB. Okay, so this D means a small B field generated by a small segment. So we just call it dB. Okay, so actually it's just a B field. Okay, but a B field generated by a small segment, so we just call it dB, and then so we just integrate along this wire, and then finally it becomes a capital B. Okay, so nothing special for this D. Okay, so the field dB produced at point P at a distance R. Okay, so the distance is actually this one, from this small segment of current to the point we concern, and then by current length element, ds turns out to be something like this. Okay, so this is a scalar form, so we have a dB on the left side, and then we have mu 0 over 4 pi. Mu 0 over 4 pi. Okay, and then we have something like I ds sine of theta. Okay, we can also imagine, okay, this sine of theta is actually comes from a cross product. And then we also have a r square in the denominator. Actually, you can somehow compare this one with the law, Coulomb's force in chapter 21. Okay, the Coulomb's force is something like F equals 1 over 4 pi epsilon naught. And then we have a Q1, Q2 over R square. So we have R square here, we have 4 pi. Okay, here we have epsilon naught, we have a mu naught, on the top. Okay, and then we have actually something times something. Okay, something times something. They are quite similar. Okay, so we can pay attention to what is this mu 0. This mu 0 is called the permeability constant. Okay, 这个叫做磁导率。Okay. 磁导率 okay. So this one is called permittivity, and then this one is called permeability, mu naught. Okay, so this value is actually 4 pi times 10 to negative 7. Okay, Tesla meter per ampere. Okay, or actually this one. Okay, why we just group out a 4 pi here? So if we just consider this mu 0 divided by 4 pi, okay, this 4 pi and this 4 pi will cancel to each other. So it remains 10 to negative 7. And similar to this one, okay, so for the E field, when we come up with epsilon naught, usually they will just like 1 over 4 pi epsilon naught, and we just call it K. When we learn about the Lorentz force or E field, something like that. Okay, and here mu naught over 4 pi also comes together frequently. Okay, sometimes maybe this mu naught will just exist independently, but usually they will just come out like a whole thing like mu 0 4 pi. Okay, 那这里有一个特性叫做这个对称性，就是电 E field 跟 B field 的对称性。那有很多式子的话，就是你把比如说类似E field 换成 B field 然后比如说把 epsilon naught 换成 1 over mu naught， OK， 类似这样的他们这样转换之后，它就会从 E field 的式子变成 B field 的式子。但这个不完全是那样的，那这个是 Coulomb's force 嘛，那这个是 B field 又不太一样。对，那但是大概是这个意思，就是这边有一个1 over 4 pi epsilon naught，它常常一起出现的。那 mu naught over 4 pi 也是常常一起出现的。那他们反正就是把 epsilon naught 换成1 over mu naught所以这个在分母，这个跑到分子去。这个还有一个 r square 这边是乘，这边是乘。OK， 类似这样。And if we try to write this formula into a vector form, so it will be something like dB vector, and then we still have this term, and then we have the current. Here we have the current. Okay, so of course this B field generated by this segment is proportional to this current, and then ds cross r hat. Okay, ds cross r hat, and then we still have r square there. So what is ds? What is r hat? Okay, so let's take a look at this figure. Okay, suppose we have a current somehow from bottom to top. Okay, and then if we try to consider the B field generated by this current acting on, for example, this point P. Okay, so what we need to do is try to cut this one into many small segment ds. So on and so forth until the end. And then for each segment of ds, we try to calculate the dB generated by each segment, and then finally we add all this dB together using an integration. Okay, just as what we did before. Okay, so in this case, for example, for this ds, okay, if you know how to calculate this ds, you should be able to calculate the others. Okay, so let's focus on this one. And as much as this current is going from bottom to top, okay, so and for this ds, okay, the ds vector is actually the tangent line at this point. And then, of course, for the tangent line, it can be either pointing to this way or the opposite way. So, yeah, so this vector also follow the direction of the current. Okay, so we have a ds or I times ds pointing to this direction, as shown in this blue arrow. Okay, and for the R is actually from this ds, okay, as much as it is so short, so we consider it's a point. Okay, so we try to connect this ds to the point we concern. This is actually R. Okay, this is actually the R. And then R head is actually the unit vector, the unit vector, yeah, pointing to this direction from ds to point P. Okay, so in such a way, we need to calculate ds cross R head. Okay, so ds. Okay, ds is pointing to this direction, and then R head is pointing to the right side. Okay, so we use a right-hand rule. Okay, you cross to the right side, and then your thumb is pointing into the page. Okay, so it actually tells you that db is actually pointing into the page. And this law is called the law of Biot-Savart, law of Biot-Savart, or sometimes we can just call it Biot-Savart law. Biot-Savart law. 那就是这个意思啊，它是一个定律了，所以是没有证明的，定律是没有办法证明的。那就是说，这个世界上现在到目前就是发现这个到现在可能已经100多，快200年嘛，应该没有200年吧，但是应该有100多年。那没有出现过违反它的情况，那它应该就是真的，就是大概是这么一个意思。Okay, so actually the next thing is to actually apply the Biot-Savart law for some other structure, Like for this one, this one is very, very useful, or it will occur many times later on. Okay, so this is really important. So for this case, it says for a long straight wire. Long straight wire 就是长的直的导线，长多长是 how long is actually infinitely long. Okay, 是无限长的 infinitely long. Okay, 就是无限长的，它就叫 long straight wire. Okay, and then 当然是直的。Okay, and then carrying a current I, the Biot-Savart law gives for the magnitude of the magnetic field at a perpendicular distance out from the wire. Okay, so the closed form solution is actually B equals mu naught I over 2 pi r. Okay, so it will occur very, very frequently. Okay, so probably you should be able to remember it. Yeah, okay, and actually the case is like, okay, suppose this one is the wire. Going into the page, I mean the current is going into the page, and this wire is infinitely long. Okay, so it will generate B field with this magnitude. Okay, so actually here if we just give a fixed current I, okay, so this is a constant, mu naught is a constant, 4 pi is a constant. So which means that the speed field is inversely proportional to R. Okay, the speed field is inversely proportional to R. So which means that for the region close to this wire, the B field is stronger, and then if it is going farther and farther away, then the B field becomes weaker and weaker. Okay, and it's inversely proportional to R. And actually, how can we determine the direction of the B field? Is again the right-hand rule, all the way right-hand rule. Okay, so you use your thumb pointing into the page, just follow the direction of the current, and then your finger will be follow the direction of the B field. Okay, something like this. So in this case, the current is going into the page, so the B field is actually clockwise. Okay, clockwise, 顺时钟 clockwise， 逆时钟是 counterclockwise. Okay, so here we have another one, which is still useful, but not occurred as frequent as this one. So it says likewise for the semi-infinite straight wire， 就是只有一半是无限的长的一个导线，所以它意思是指从零到正无穷是有，从零到负无穷是没有，是这样是半无限。Okay, the magnitude of the magnetic field at the perpendicular distance out from the wire. Okay, so it's just half of this one. Okay, and so in the next page we will show you the how we can derive this one using the integral. Okay, so this is the way to calculate this one. Okay, so here we have a long straight wire. Okay, and then what we would like to find the B field at this point P. Okay, so here let's try to define. Okay, this axis. This axis is actually, this is the S-axis. This is the S-axis, and this is the zero. This is the zero. So as much as we assume it's infinite wire, so it is from negative infinity all the way up to the infinity. But actually, you can consider this half and this half. The positive half and the negative half will give you the same value and actually the same direction at this point. So so we only just need to calculate half of it, and then we multiply it by 2. And then give you the correct answer. So using the Biot-Savart law, it will be like dB equals mu naught over 4 pi I ds sine of theta over r squared. Okay, so this is the scalar form of the Biot-Savart law, and then the total B field at point P, B originally should be integrating from negative infinity to infinity dB. And then so we just simplify it by calculating half of it, and then we multiply by 2. So we only integrate the dB from 0 to infinity. And then we just plug in this dB into here. So mu naught over 4 pi is a constant, and then we can put it out, and then this 4 and this 2 cancel. So we only have a mu naught over 2 pi. I is also a constant. And then ds is here, and then sine of theta is inside, and then r squared is also inside. Okay, although it's somehow like, we integrating ds, this is not s, this is not s. Why not we just put it out and then but actually this theta is actually depending on s. Also this r squared also depends on s, so we cannot just put this thing outside. They are actually the functions of s. Okay, so we just try to express this theta and r in terms of s, and then finally we can do this integration. Otherwise, if we just put it out and then integrating ds from 0 to infinity, or give you an infinity, but this is clearly wrong. Okay, so here we try to find the expression r. Okay, so this is the original point, and then this is the point we concern, and then for example we consider a segment here. This is actually ds. Okay, so r is actually from this ds to this point P. So this is R, and this is S. This is S from 0 to this point S. And then this is the R. Okay. This is R from this Y to the point we concern. Okay, the perpendicular distance. Okay, so yeah, so this is a right angle triangle. So we have R equals square root of S squared plus capital R squared. Okay. And actually the theta is actually ds cross r, ds cross r. So the theta is this one. Okay, so this is yeah, so this is theta, and then this one will be pi minus theta. Yeah, but hopefully sine of theta equals sine of pi minus theta. Okay. And actually sine of theta is this r, capital R divided by small r. So we just put this square root here. Okay, so sine of theta have this expression. And so it's a function of S, and then capital R should be a constant. Okay, so in this case we can just plug in R and sine of theta into here. So R, so here we have R squared. So this is actually R squared, and then multiplied by this one. So altogether we have R S squared plus capital R squared, and then the whole term to the 3/2 power. And then we also have this R, capital R here. And then we do the integration of ds. Okay, so okay, so actually this integration, yeah, this integration is somehow a little bit complicated. You need to actually assume that S is actually R times tangent of theta, something like that, and then you do some change of variable, U substitution, something like that. Okay, and then finally you can get this integration to be this one, and then you finally evaluate it from 0 to infinity. So if you plug in 0, okay, plug in 0 will be nothing but 0, and then put in infinity will be 1. Okay, this is infinity, this is infinity, and then take the square root. This is the constant, so finally it becomes a 1. Okay, so finally this whole term becomes 1, and then so which means that B equals mu0 I over 2 pi r. Up till now, any questions? 有没有问题？ OK， 所以这个式子的话，后面会常常会用到了。那这个是 B 等于 mu I 除以2 pi r。那这是一个无限长导线，无限长的直的导线产生的那个磁场就是正比于电流，然后反比于那个距离And then this one is have a similar form but not quite the same. Okay, so this says the magnitude of the magnetic field or the B field at the center of a circular arc， 就是一个圆弧的中心点，它会产生一个 B field。OK， 所以这个是弯的，这个是一个圆弧，这个是一个圆的一部分，一个圆弧of a radius capital R。Center angle phi 就是圆性角 okay, in radians. Carrying current I is actually this one. It's actually this one. Okay, so the derivation is simple because yeah, as much as this distance is a constant. So using the Biot-Savart law to evaluate this b is something like we integrating a constant. So it turns out to be an angle. So finally, we have a mu 0 I phi over 4 pi r. And one special case is that if it is a whole circle, which means that this phi is actually 2 pi. And if we substitute phi to be 2 pi, then it turns out to be mu 0 I over 2r. Okay, so it is quite similar to the previous one, yeah, but we don't have this pi in the denominator. So be careful, there are different things. This one is for the long straight wire, okay? This one is for a circle. This one is for a circle with a current. So it will generate B field at the center. So the magnitude of this B field have this magnitude. Okay, so what is the direction? What is the direction at this point? Into the page or out of the page? Okay, still using right hand rule. Into the page or out of the page? Out of the page. Okay. So you use your finger following the current of following the direction of the current. Okay, your thumb will be pointing out of the page, which is the direction of the B field. Or you can use another way of using the right hand rule. Yeah, for this case, the right hand rule is something like this. You use your finger, or use your thumb follow the direction of the eye, and then, your four fingers, at this point will be pointing out of the page. You can use the right hand rule for both ways. Okay. Okay, so here we have a sample problem. So it says the wire carrying a current I and consists of a circular arc of radius capital R and central angle pi over 2 radian and two straight sections whose extension intersects the center C of the arc. What B field does the current produce as C? Okay, so this is the point C, which is the center of this arc. And then the current is from here, the segment 1, segment 3, segment 2. Okay, so here we clearly can see that this segment will not generate any B field at point C because, suppose we cut out one segment of DS. DS is essentially pointing to this direction, and R is actually in this direction. And so as R hat also points to this direction. So DS and R hat points to the same direction. So the cross product will be 0. So dB1 will be 0. And and similar for segment 2, dB2 also equals 0. So these two segments will generate no E field at point C. So the only thing will similar. So the only part will generate the B field at point C is actually the segment C. So for the B3 is actually mu 0 I and then times phi over 4 pi R. Okay, so 4 pi R, So actually this phi is pi over 2, so it is nothing but pi over 2 and then 4 pi R. Okay, so finally pi and pi cancel, so it turns out to be mu 0 I over 8 R. Okay, as much as it doesn't tell you the value of I and capital R, so we don't try to substitute the value of mu zero there. So to make this answer to be more elegant. Okay, and then we have another one. So here we have two long parallel wire carrying currents I1 and I2 in opposite directions. What are the magnitude and direction of the net B field? Net B field at point P. Okay, point P here. Assume the following values I1, I2, and D, and then this is a right angle. Okay, so B1 is actually mu 0 I over 2 pi capital R. And then B2 is actually mu 0, I1 here, okay, mu 0 I2 over 2 pi R. Okay, so just make use of the formula before. And as much as this is a right angle triangle using the Pythagorean theorem, we know that R is actually D over square root of 2, okay, which will be 5.3 over square root of 2, which is 3.75 centimeter. Okay, so in such a way, this one should be B2. Okay, so the total B. Okay, so here we have B1 point to this direction, B2 points to that direction. Okay, so maybe we can somehow know that why B1 points to that direction. Okay, so actually I1 points to is pointing out of the page. Okay, so your use of thumb pointing out of the page, your finger at this point P. Okay, finger at this point P will be point to the top left. Okay, point to the top left for B1, and then I2 is pointing into the page. So you use your thumb pointing into the page, and then your forefinger and point P will be pointing to the top right. Okay, that's shown in here. So B1 points to this side, B2 points to this side. So the total B, okay, we can also use the Pythagorean theorem so that we know B, okay, B is actually square root of B1 square plus B2 square. Okay, so we just have mu 0 over 2 pi R, and then square root of I1 square plus I2 square. Okay, so it is nothing but 4 pi times 10 to the negative 7 over 2 pi times 0.0375 times square root of 15 square plus 32 square. So the answer will be 180 mu Tesla. Okay, so this is the magnitude of the B field, and then still we need to know the angle, Of course, what we can do is, we can try to decompose B1 on x-axis and y-axis, and also we decompose B2 on x-axis and y-axis, and then we add the x-axis components, and then we add the y-axis component, and then finally we can get this angle. But a quicker way to do this is to find this phi, and then we add it by 45 degrees. We already know that this is 45 degrees. Okay, this is also 45 degrees. So we can just find this phi quickly using phi to be arctangent of B1 over B2. So it will be actually arctangent of I1 over I2. Okay, we can just plug in this one and this one into here. So finally, all the terms cancel. So finally, we only have I1 over I2. So it will be nothing but arctangent of 15 over 32, which is 25.1 degree. Okay, so finally theta, this is theta. Theta will be 5 plus 45 degree, which is 25.1 degree plus 45 degree, which is 70.1 degree. Okay, so this is